Dear students, we are on the CEC Guru lecture and we are discussing the electronic bridges. In the electronic bridges, we are discussing the AC bridges as well as the DC bridges. In the DC bridges, we discuss the Wheatstone bridge as well as the Kelvin bridge. In the AC bridge, we are discussing the Anderson bridge. Anderson bridge are used to measure the unknown inductance. So, in this series, we are discussing the to find out the unknown resistance, we are using the Anderson bridges. So, in the Anderson bridges, we just know that how we can get the unknown inductance, and the value of unknown inductance is Lx is equal to CR3 by C4 R into R4 plus R2 plus R2 into R4. This is the equation through which we can find out the unknown inductance, and from this equation we can see there is no small r1 and no capital R1. So, the inductance is independent of the value of R1 and R1, small r1 and capital R1. So, this is the equation to measure the unknown inductance. So, in this a phasor diagram of the Anderson bridge. So, we draw the phasor diagram, the phasor represent of the Anderson bridge, how it's working. You see the various point here, that the current and the potential difference between the 2 points. So, from the bridge circuit it is clear that the current through the arm Wx, that is I1, and the voltage drop at the arm xy, that is E3, are in the same phase. Now, you see I1 and E3 are in the same phase. From this diagram we can see. Then we can see that this show the horizontal axis. In the above figure we have seen that these are the horizontal, that represented by the horizontal axis. Now, under the balance condition, we know that the drop across xy and oy must be equal. At the 2 points, if we take the balance condition, then the drop across the xy and oy must be equal. So, the current flowing in the arm Wx causes the drop, that can be represented as I1 R1 plus small r1, and the phase with the arm current is the I1. So, due to the balance condition of the bridge, this current flows through the arm x and y. So, through the arm x and y, I1 current will flow. Now, we can take the drop across the another point, that is yz, that is the E4, and it is equivalent to the sum of the drop at the OZ and the OY, and that will be represented as IC divided by omega capital C and IC into R respectively. So, thereby showing the current I4 will be in the phase with the drop across YZ, that is E4. So, phasor summation of the drop across the Wx and xy, or the drop across the yz and the zw, provides the supply voltage, and that voltage will be used for calculating the unknown inductance. So, what are the advantages of Anderson bridges? The bridges is composed of the fixed capacitor, that makes the determination of inductance quite easy. So, one can find the accurate value of the capacitance in accordance with the inductance by using the Anderson bridges. In the another advantages, it is quite simple to find out the balance point in the Anderson bridge. Another bridge is the Maxwell bridge. This is also a AC bridge, and that bridge used for measurement of the self inductance of the circuit, and that bridge is known as the Maxwell bridges, and it is advanced form of the Wheatstone bridge. The Maxwell bridge works on the principle of comparison, that is the value of unknown inductance is determined by comparing it with the known value or the standard value. So, by using the Maxwell bridge, we can measure the self inductance on the principle of the comparison of the unknown resistance. Now, what are the type of the Maxwell bridges? Two methods are used for determining the self-inductance of the circuit. What are these two types? First is the Maxwell inductance bridge and second is the Maxwell inductance capacitance bridge. These two are the types of the Maxwell bridges. So, Maxwell inductance bridge, what is this? This is used for measurement of the unknown resistance by comparing it with the known value of the standard self inductance. So, in such type of bridges, the value of the unknown resistance is determined by the comparing it with the known value of the standard self inductance. The connection diagram of the balance Maxwell bridge is shown here. You see here that this is a Maxwell inductance bridge, and here inductance are used here. R1, L1, R3, R2, R3, and variable resistance are here R3, and variable inductance is the L2. So, the L1 is unknown inductance of the resistance R1, R1 is also unknown resistance, and L1 is the unknown inductance. So, variable inductance L2 is a variable inductance of the fixed resistance R1. Here you see here L2. Now, R2 is a variable resistance connected in the series with the inductors L2. And next is R3 and R4 are the known inductance resistance. Now, at the balance we can write it as L1 is equal to R3 by R4 into L2. When the two L1 and L2 both the inductance are balanced, then we can write it as L1 is equal to R3 by R4 into L2, and we know that R1 is equal to R3 by R4, R2 plus R2. Then the value of the R2 and R4 resistance varies from the 10 to 1000 ohms. So, with the help of the resistance box, we can vary the value of the R3 and R4, that is a variable resistance. Sometimes for balancing the bridges, the additional resistance is also inserted in the circuit to balance the bridges. In the phasor diagram of the Maxwell inductance bridges, we can have this one. You see here E3 is equal to E4, and we can write it as I1 R1 is equal to I1 R2 plus small r2, and I1 R3 is equal to I2 R4. E1 and E1 is equal to E2, that is the balancing condition, and we can balance the two values. I1 omega L1 is equal to I2 omega L2. It is very simple to understand that the phasor diagram of the Maxwell inductance, and we can write it as I1 R1 is equal to I1, R3 is equal to R2, I4, all are the balanced. So, Maxwell inductance another type of Maxwell bridge is the Maxwell inductance capacitance bridge, and this type of bridge is used for measurement of the unknown resistance and with the help of the standard variable capacitance. So, so if we talk about the connection of the Maxwell bridge, then we can see here on the right hand side you are seeing the different type of the arrangement shown here, that capacitance is arranged with the resistance. So, the another circuit is same, but here on the right hand side the arm C and D is changed as we add the capacitance C4 here. So, now the L1, again the unknown inductance of the resistance are R1 is the variable inductance of the fixed resistance small r, R3, R2, R3, R4 are the variable resistance connected in the series with the inductors L2, and C4 is known as the non-inductance resistance that you see here, that the C4 is the unknown capacitance. So, that unknown, this is the known non-inductance resistance. For balance conditions, we can write it as R1 plus j omega L1, which is R4 divided by 1 plus j omega C4 R4, and as it is variables, C is variable, so is equal to R2 and R3 in the valence condition. R1 R4 is equal to j omega L1 R4 is equal to R2 R3 plus j omega C4 R4 R2 and R3, all are valence. By separating the real and imaginary part, finally we will get R1 is equal to R2 R3 divided by R4. That is a that we can measure the inductance here. L1 is equal to R2 R3 and R4, where we use the then the above equation shows that the bridges have the two variables R4 and C4, which appears in the one of the two equation, and hence both the equations are independent. So circuit quality factor can be written as Q is equal to omega L1 by R1, that is omega C4 R4, and these C4 and R4 are two variables which is in equation. Now if we talk about the phasor diagram of the Maxwell inductance capacitance bridge is shown here. You see here that we can have the E2 is equal to I1 R2, and it is I1 omega and L1. Now you see I1 R2 and IR. E3 is equal to, that will be the I2 R3 is equal to E4, that is IC by omega C4, which is equal to I R E4. So the in the phase diagram we can see here, then we are having the different values of IC, I2, and balancing condition here is the potential difference we are measuring. And what are the advantages of the Maxwell bridges? Maxwell bridge having the advantages that it is used for this is the balance equation of the circuit is free from the frequency, then we can use the Maxwell bridge. So both the balance equations are independent of the each other, as we see that it is the frequency is not required here. The Maxwell inductor capacitance bridge is used for the measurement of the high range of the inductance. We can measure the high range of the inductance. What are the basically what are the basic disadvantages of the Maxwell bridges? Maxwell bridges, capacitance bridges requires a variable capacitance, which is very expensive, and thus sometimes the standard variable capacitors is used in the bridges. So the putting the value of the capacitance, it will make it the effective. So bridge is only used for the measurement of the medium quality coils, and because of the following disadvantages, Hayes bridge is used for the measurement of the circuit inductance, which is advanced form of the Maxwell bridge. So in the next we discuss the Hayes bridges. So Hayes bridge is the advanced or the modified form of this Maxwell bridges. What is the Hayes bridges? Hayes bridges used again for determining the self inductance of the circuit. The bridge is the advanced form of the Maxwell bridge, and the Maxwell bridge is only appropriate for measuring the medium quality factor, but here measuring for the high quality factor we use the Hayes bridge. And what is this Hayes bridge? Hayes bridge is the capacitor is in the Hayes bridge, the capacitor is connected in the series with the resistance. So the voltage drop across the capacitance and the resistance are varied. So the and in the Maxwell bridges, the capacitance is connected in the parallel with the resistance, but here in this Hayes bridges the resistance the voltage drop across the capacitance and the resistance are connected in the series. So the magnitude of the voltage pass through the resistance and capacitance are equal. So what is the construction of the Hayes bridge? In the Hayes bridge, the unknown inductor, that is L1, is placed in the one of the arm, and here we put in the arm AB along with the resistance R1. The unknown inductor is compared with the standard capacitor, that is the C4, and connecting across the arm CD. The resistance R4 is connected in the series with the capacitor C4, and this time we are connecting in the series. Previously in the Maxwell we connected in the parallel. So the other two non-inductive resistors R2 and R3 are connected in the arm AD and BC respectively. You see in the diagram here that in the arm D and C, here we connect the resistance and capacitor in a series. So that is C4 and R4. Others are same, others are arranged, and you see on the arm A and B, R1 and L1 are arranged in the series, and R3 and R4 are the known resistance. So this is the Hayes bridge that is used for measuring the self inductance. Here in this, C4 and R4 are adjusted for making the bridges in the balance condition. So on the right hand side, the D and C, we arrange the C4 and R4 for balancing the bridges. When the bridge is in the balance condition, no current flows through the detector. Then we can get the null deflection, and which is connected to the point B and C respectively, and we can get the null deflection in the galvanometer. The potential drop across the arm AD and CD. This is AD. On the left hand side you see the potential difference between the arm AD and CD and CD are equal and similar. The potential across the arm AB and BC are equal. Here AB and BC are equal. So by using this we can get that L1 is the unknown inductance having the resistance R1, and R2, R3 and R4 are the known inductive resistance, and C4 is the standard capacitor. At the balance condition we can write it as R1 plus j omega L1 into R4 minus j omega C4, that is equal to R2 and R3. R1 and R4 is plus L1 by C4 plus j omega L1 R4 minus j R1 divided by omega C4 is equal to R2 R3. By separating the real and imaginary part, we can have the two equations. First is R1 R4 plus L1 C4 is equal to R2 R3, and L1 is equal to minus R1 divided by omega square R4 and C4. By solving the above equation, we can find out L1 and R1, and moreover we can find out the quality factor of the coil. So L1 is equal to R2 R3 C4 1 plus omega square R4 square C4 square. Here we are balancing the two values R4 and C4. Now R1 we can get omega square C4 square R3 R2 R4 divided by 1 plus omega cube R4 square C4 square. In this vector, in this value, in this manner we can find out the value of the inductance and resistance L1 and R1, that is unknown to us, and the quality factor of the coil, that will be Q is equal to omega L1 divided by R1, or we can write it as equal to 1 by omega square C4 R4. This is the equation of the unknown inductance, and the capacitance consists frequency term, here we see. And thus the finding the value of the unknown inductance, the frequency of the supply must be known. For the high quality factor, the frequency does not play a very important role. So Q is equal to 1 by omega square C4 R4, that we will take. Substituting the value of the Q in the equation of the unknown inductance, we can have L1 is equal to R2 R3 C4 divided by 1 plus 1 divided by Q square. So for the greater value of the Q and 1 by Q is neglecting, and hence we can have the equation L1 is equal to R2 R3 and C4. That will be the if we talk about the phasor diagram of the Hayes bridge, so the Hayes diagram, the phasor The phasor diagram of the Hayes bridge is shown in the figure. We will taken in the next slide. The magnitude of the phase of the E1 and E4 are equal, and hence they are overlapping each other and draw on the horizontal axis, the E3 and E4. You see here E3 is equal to E4, they are on the horizontal axis. And you see that the current I1 flow through the purely resistive arms BD, and the current I1 and the potential, that is E2 is equal to I2, that is E3 is equal to I3 R3, and are in the same phase. I3, you see here, E1 is equal to E2, E3 and E4, and here the current flow in the same manner, that I1 R1 is equal to that here I3 and R3. So the current passes through the arm AB, produces a potential drop, that is I1 R1, which is also the same phase of the I1, and the total voltage drop across the arm AB is determined by the adding the value of I1 R1 and omega L1 or omega I1 and L1. So the voltage drop across the AB and AD are equal. Here you see AB and AD are equal. So we can have the voltage drop E1 and E2, which is equal in the magnitude and in the phase, hence overlap each other. So the current I2 and the E3 are in the same phase, as we can have it. So the voltage drop across the resistance C4 and R4 gives the total voltage drop across the arm CD. So the sum of the voltage E1 and E3 or E2 and E4 gives the voltage drops, capital total voltage, that will be the E. What are the advantages of the Hayes bridge? The Hayes bridges give a simple expression for the unknown inductance, and these are suitable for the coil having the quality factor greater than that of the 10 ohms. It is also used to calculate the quality factor in a simple manner, and the Hayes bridges uses the small value of the resistance for determining the Q factor. What are the disadvantages of the Hayes bridges? The only disadvantage of this bridge is that it is not suitable for the measurement of the coil having the quality factor less than that of the 10 ohms. So the quality factor is a parameter which determines the relation between the stored energy and the energy dissipated in the circuit. So any bridges efficiency can be measured by using the quality factor. If the quality factor is in the range, then the bridge works better. So quality factor is the best parameter for determining the relation between the stored energy and the energy dissipated in the circuit. Thank you very much.